Hello, well, welcome again to my reading session. Today I'm going to read about this what is article from Hugging Face. I looked at in the topic only, have not read it, so it will be quite a new for me to get the general idea of what the current technology on this topic is about here. Scaling real-time voice agents with Cache-Aware Streaming ASR. This article is about the real-time voice agent. Okay, now let's read it. In voice AI interaction, we have long been trapped by the familiar trade-off: speed versus accuracy. Traditionally, real-time automatic speech recognition relies on buffered inference, a workaround where system repeatedly reprocess overlapping audio windows to maintain the context. It is the computational equivalent of rereading the last few pages of the book every time you turn the pages. NVIDIA Nemotron Speech ASR, a new open model built specifically for real-time voice agent, break this cycle. Built on this fast conformer architecture with 8x downsampling, it introduces the cache-aware technology to process the new audio deltas by reusing the part of the computation rather than the recalculating them. It achieves up to 3x efficiency than the traditional buffer system. In this post, we will explore how cache-aware architecture defines the limit of real-time voice agent and show real-world results from daily and model for high concurrency, low latency voice agent workloads. The challenges: why streaming ASR breaks at this scale. What are the challenges? Let's read about it. The most system labeled as streaming ASR were designed for real-time interaction at a scale. The Nemotron speech collection, part of the NVIDIA Nemotron family of open models, enable the developer to plug speech into the custom agentic workflow. Buffered inference is not a real streaming. In the many production systems, streaming is implemented using the buffered inference. Audio is compressed into the sliding window and new window overlap with the previous one to preserve the context. While this procedure produce the correct transcripts, it is fundamentally inefficient. The model repeatedly reprocesses that has already been processed, sometimes several times over, just to maintain continuity. Overlapping windows waste compute. This overlap means redundant computation at every step. The same audio frames are re-encoded, the same attention context is recomputed. GPU works scale faster than the actual audio stream. At low concurrency, this inefficiency may be tolerable. At scale, it becomes expensive and fragile. Latency drift breaks the conversational agent. Main problem is here. As the number of concurrent streams increases, the buffered input often hit the scaling cliff. Latency begins to drift. Response arrive later and later relative to the spoken audio. This drift is not a scheduling issue, but the hardware resource problem. Because the buffered inference repeatedly recomputes the overlapping context, GPU memory fills the redundant activation and the intermediate states. As the memory pressure increases, the system increasingly constrained, forcing the slower execution, reduced batching efficiency, or outright throttling under the load. For conversational agent, this is fatal. Even a small delay disrupts the downstream tasks such as the tron taking and intervention handling, making interaction feel unnatural. Over time, the system lags so far behind the real speech that it can no longer support real-time dialogue, or it fails to scale at the scale when strict latency threshold must be maintained. This is the core limitation of legacy streaming ASR. it works in isolation but breakdowns under the computational and latency pressure of the real-world multi-user system. What is the solution? The solution, the Cache-Aware Streaming ASR for lower latency, linear scale and predictable cost. Nemotron Speech ASR introduces a new generation streaming architecture that replaces the buffered inference model of legacy system. It caches It is cache-aware design that enables the real-time, high-concurrency voice agent with the stable latency, linear scaling, and significantly higher GPU throughput without compromising the accuracy or robustness. Key benefit: end-to-end, lower end-to-end latency, reduce the ASR processing time and redundant computation, minimizing the end-to-end latency across the voice agent pipeline with the LLM reasoning and the text-to-speech. High efficient high concurrency, maintain the near flat latency even as concurrency increases by up to 3x, avoiding the rapid degeneration seen in the buffer system. In practice, latency grows sublinearly. It grows and does not meaningfully budge until concurrency is significantly higher. Linear model memory scaling. Cache-aware streaming prevents the memory blowups by enabling the predictable performance and stable batching. High GPU efficiency and lower cost maximize the parallel stream throughput per GPU, reducing the overall cost per stream. Inside the Nemotron Speech ASR, fast kernel and 8x downsampling. Nemotron Speech ASR is built on the fast conformer RNNT architecture. I didn't know about this architecture. It's quite new to me. Okay, similar to the previous NVIDIA Prokit ASR model, optimized to end-to-end streaming inference. A key innovation is 8x downsampling using depth-wise separable convolution subsampling compared to the traditional 4x auto. The encoder processes significantly fewer tokens per second, reducing the VRAM footprint and increasing the throughput across the GPUs. Key engineering specs. Architecture: fast conformer with a 24 encoder layer and RNNT decoder. Parameter 600 million, optimized for high throughput NVIDIA GPU. Input is 16 kHz streaming input. Output is streaming English text with the punctuation and capitalization. Dynamic runtime configurable latency of 80 millisecond, 160 millisecond, and 560 millisecond, and 1.12 second. No retraining is required. We can directly use this model for the stream. The audio. How cache-aware streaming works. Instead of re-encoding the overlapping audio windows, Nemotron Speech ASR maintains an internal cache of encoder representation across all self-attention and convolution layer. When the new audio arrives, the model updates their cache rather than recomputing the previous context. Each frame is processed exactly once without the overlap or redundancy. This design eliminates the two biggest problems of buffering inferences: wasted computation from the reprocessing same audio, latency drift as concurrent stream increases. The result is predictable end-to-end latency and linear scaling even under the heavy load. What is cache-aware streaming pipeline? Here is the incoming audio sample continuous stream, which is a chunk splitter, means incoming audio is split into chunks 80 millisecond per frames, and feature buffer means from the chunk from the audio streams chunk the feature is extracted, I think. And context manager, which manages the context for the slot and cache lookup, and cache is being updated here, means once the incoming sample goes, it updates the cache and it goes to the cache-aware fast conformer encoder, then CTC, RNNT, TDD decoder. There are it is the different type of decoder, and it gives the text output. And when new stream comes, the previous stream is being look up from the cache, from the lookup table from the cache, and being computed. I think that is what it is. Okay, let's read it to get the clear picture. Figure 1. Cache-Aware Streaming Pipeline. The streaming ASR architecture utilizing the cache-aware conformer encoder and context manager to maintain the encoder state without redundant computation. Prediction, chunking, and audio buffer. Audio buffer, left context, prediction chunk, current frame plus look ahead. Step 1, frame 1, frame 2, frame 3, frame 4, frame 5. Step 2 means frame 4 and frame 5 from the previous block. There is a frame 6 that is being predicted, and assume left context is equals to 2, look ahead is 4, means using the 2 they are looking for the 4th frame that needs to be generated, or what. Prediction, chunking, and audio buffer. Detailed view of the audio buffer logic demonstrating the how prediction, chunk, and look ahead frames are processed in successive steps to ensure predictable memory behavior. From more details, check out the paper. Okay, I'll look into it, but not now. Results: throughput, accuracy, and speed at scale. Throughput that holds under the load. The architectural efficiencies of the cache-aware streaming translate directly into the significant throughput gain. On the NVIDIA ES100 Nemotron Speech ASR support 560 concurrent streams at 320 millisecond chunk size, a 3x improvement over the baseline. 180 streams. Similar gains are observed across the stack. NVIDIA RTX 5000 delivers the 5x higher concurrency, while NVIDIA DGX B200 provides the 2x throughput across the 660 millisecond and 320 millisecond configuration. Crucially, the benchmark validated the system stability, maintaining the zero latency drift even when pushed to peak capability, enabled by bounded memory growth and cache reuse rather than the repeated computation. Nemotron 3x improvement in the current supported stream. Concurrent supported stream, here is the Pratik CTC 1.1 baseline and Nemotron ASR. It is nearly at 180, nearly at 200, and for the Nemotron ASR, the concurrent stream is nearly 600, about 460. Concurrent stream, yeah, it is 3x nearly. The throughput expansion of NVIDIA ES100 showing a 3x increase in concurrent support stream at a 320 millisecond chunk size compared to the previous baselines. The result highlight why demos and proof of the concept should account for the scale and cost, ensuring the low latency holds at the target workload and support the sustainable business case. Accuracy where it counts. Latency WER trade-off. Most of the ASR leaderboard evaluate the model in offline model, which hide the real world cost of the low latency. In streaming, ASR accuracy and latency are inseparable. Nemotron Speech ASR provide the dynamic runtime flexibility, allowing the developer to choose the right operating point at the inference time, not during the training. The chunks latency increases from 0.16 second to 0.56 second. The model captures the additional phonetic context, reducing the WER from 7.84 to 7.22 while maintaining the real-time responsiveness. Here is the graph for the Nemotron Speech ASR scale accuracy with the phonetic context. X-axis is chunk size and y-axis is number of concurrent streams. For the NVIDIA Pratik, which is represented by green, maximum is 640 stream concurrent stream at 0.56 second chunk size, but the same with the for the same chunk size, The NVIDIA Nemotron Speech Streaming ASR 0.6 billion gives 900 concurrent stream with the error rate improving from the 7.842 to 7.22, which is quite remarkable if we deploy in this scale. Figure 4, Nemotron Speech ASR consistently outperforms CTC baseline light green, increased sound latency, improve the WER by capturing the richer phonetic context, faster time to final transcription. Nemotron ASR also delivers the industry-leading time to final transcription across both local and API-based alternative. Nemotron Speech ASR 24 millisecond medium, alternative local L40 GPU 90 millisecond, alternative models API-based 200 plus millisecond. Critically finalization time remains stable even for the long utterance, essential property for the real-time agent. What is the real time? Here is the example of real world validation. They keep some pipecat playground. Okay. Model validating minimal latency drift at scale. In collaboration with the model, Nemotron Speech ASR was evaluated using asynchronous WebSocket streaming to measure the latency stability at scale. Evaluation setup: ASR Nemotron Speech ASR sharpening configuration 500 millisecond latency on NVIDIA ES100 GPU, load 127 concurrent WebSocket client, duration 3-minute continuous stream. Load is 127, connection was at the same time. Yeah, and here is the graph validation of latency, which is increasing. Client time syncron through the transcript timestamp. Aggregate ASR timing analysis while running the 127 concurrent WebSocket client, demonstrating the perfect linear timestamp synchronization stable medium delay of 182 millisecond, validating the minimal latency drift at scale. At 127 simultaneous clients, Nemotron ASR model maintain the stable in latency with the minimal drift during the 3-minute stream. For voice agent, this difference is decisive. Even a few seconds lag breaks on staking and render the interruption handling impossible, as shown below. Nemotron ASR achieves the level of efficiency previously thought impossible in the real time. Voice AI, the 160 millisecond latency setting showcases the model raw speed, delivering the fastest time to final transcription available for high-stake real-time interaction. What makes this architecture truly revolutionary is its intelligent resource management. When set to 160 millisecond, it pushes the absolute boundaries of hardware concurrency, but Nemotron has unique phase flexibility to shift from the high capacity model 560 millisecond to 1.12 latency that flatten the curve entirely. This ensures that even at the massive enterprise scale, user experience zero drift, human-like responsiveness that proprietary APIs cannot simply sustain. Now, delete into agent performance. Delete builds a real-time audio and video infrastructure for developer creating the voice first and multimodal application, from AI meeting assistants and customer support agents to real-time collaboration tool. For daily users, predictable low latency speech pipelines are critical. Delay jitters directly translate into the unnatural conversation and poor user experience. To evaluate the real world performance, daily integrated Nemotron ASR is ASR into the full production style voice agent pipeline consisting of ASR, Nemotron Speech ASR, Brain, Nemotron 3 Nano 30B, Voice, MagPi TTS multilingual with 7 languages and 5 voices, orchestration library, Pipecat by Delhi, platform model DZX Spark RTX 5090. In this system, Nemotron ASR achieve a median time to final transcription of just 24 milliseconds, independent of authorized length. Long audio segments finalize as quickly as short ones, an essential property for interactive agent where user may speak unpredictably. In the full voice-to-voice loop completed in 900 milliseconds for local deployment. This enables the natural tone-based conversation with stable, predictable latency, even under the sustained interaction. Exactly the behavior the daily developer needed to build the responsive production-grade voice agent that user can trust. Conclusion of new baseline for real-time voice agents. Most ASR developed systems were originally designed for the offline transcription and later adapted for streaming use cases. As these legacy approaches are pushed into the high concurrency, their limitation becomes clear, surfacing this latency, rising infrastructure cost, and degraded user experience. Voice agent place fundamentally different demands on the speech recognition. Streaming and real-time interaction can no longer be afterthought. They must be treated as the first-class design goal. Meeting the complexity of the voice first application require the ASR architecture that are purpose-built for the low latency, scalability, and sustained performance under the load. Cache-Aware Streaming sets this foundation with the Nemotron Speech ASR voice agents no longer needed to trade speed for the accuracy or scalability by limiting the redundant computation and enabling predictable linear scaling, and model delivers 100 millisecond responsiveness, stable latency under the high concurrency, and production ready at scale. Nemotron Speech ASR establishes a new baseline for the real-time voice AI agent. And here is the if you want the step to use it, you can clone and run on the Hugging Face. Enable the Cache-Aware streaming inference in NVIDIA Nemo. Deploy the NVIDIA Nemotron ASR in a model. Build the local voice agent using the daily framework. Yeah, this is one of the community. I like it a lot because it compared the 1.1 billion model with the 600 million. On this is misleading as demonstrating the added value of caching mechanisms will be done on the model of the same size. Otherwise, the half of the 3 cache can could be attributed to the sole parameter count difference. Okay, what is the reply? Thank you for the question. This block is written from the in user perspective, focusing on why when one should use the Nemotron ASR model. For that reason, we chose to compare the model. Means this model was the article was not written by the researcher from the research point of view, but by the NVIDIA from the user point of view, why this will be used. Okay. Okay, this is for today, and thank you for watching. Okay, or is it okay? Thank you for watching.